me make sure that streaming is in progress. Yes. All right, guys, welcome everyone again. Today, we are going to talk about two topics or two papers dealing with AI agents. As you know, AI agents is the topic of AI agents is um, an area of very, very active research. There is a general belief that you harness the full power of LLMs when you use them as language agents. Now, uh, there are two papers we'll cover. One of them is called SWE Agent. SWE, of course, implies software engineer. In Silicon Valley, that's an abbreviation for software engineer, SWE. This paper is from Princeton University, and this is the open source. This is the Princeton University NLP GitHub for that SWE agents. The site, it is getting a lot of attention, at least on the East Coast. Surprisingly, I noticed that this paper around which conferences, there was literally a conference recently, has not garnered that much of citations yet. It came out a few months ago, in May 2024. Now, May means June, July, August. It seems like an eternity, and no other research paper is referred to it. Something should be, because they're taking it very, very seriously out there in Princeton, and there was quite a high attendance around this paper, I'm told. The second paper that we are going to talk about today, and this is, by the way, again, as request from the community, these two papers I was requested to cover, is XLAM. These are large action models. And this came out just about 10 days ago, a couple of weeks ago, I would say, September 5th, and has some impressive results. We'll go over it. Before I continue with that, I'll just give a very quick primer on what agents are. Agents are a topic in AI. It has been the old dream. When people think of AI, traditionally, they think of it as a core AI sitting there, or multiple instances of the AI or agents sitting there. They have access to them. If you look at the classic AI textbooks, sensors and actuators, they get information from the environment, right? What's happening in the environment. And then they act upon the environment. They reason, they think, and then they act upon the environment using actuators, right? So there is a back and forth. Basically, when AI interacts with its environment, gets input or feedback from the environment, and then when it affects the environment in any way, this loop is the basic notion of AI agents as it has existed in AI. Now, the theory of AI agents dates back surprisingly, to 1980s and 1990s. Much of the thinking had evolved quite far in the 1990s. So you can imagine that 3 decades of thinking has gone into AI agents. It is, however, only recently that with the coming of large language models, people realized that you can create very effective agents, AI agents, using language models. So these are the LLM agents. And this has spurned a whole huge area of research. If you recall, we covered the paper Simulacra. That Simulacra paper has already received, in 1 year of its publication, more than 1,000 citations from other research papers that got published in this space. It speaks to how active an area and core area of research AI agents currently are. So today we'll cover 2 papers, as I said. We'll do SWE agents. It's a simpler paper, and it's very focused. It has a core idea, which I can fairly well express, but quite a remarkable idea. It's just based on where I would say a very insightful thought. And again, as I said, the authors are almost all from Princeton. In fact, all of them are from Princeton University. So what is this thing called SWE agent? The title of this paper is Agent Computer Interfaces Enable Automated Software Engineering. So here's the core idea that this paper talks about, which I'll give you to keep in the background as a backdrop as we walk through this paper. What they're saying is, imagine that you're engaging with Linux. When you engage with Linux, if you are a fan of the command line, then you engage with Linux using the bash shell or Z shell or whatever shell that you prefer, using some shell, and the shell gives you a pretty large array of commands or tools in some sense. If you were to think of it as AI language, you would say that you are if you think of yourself as an AI or, well, human intelligence, sitting there engaging with the shell, with the operating system, the shell is your interface. You have access to a lot of tools, which are your commands, like change directory, list directory, make directory, and open a file, cat, less, so on and so forth. Set to replace something in some string with another string in a file, awk, and so on and so forth. So a bash is a pretty rich command set, pretty rich vocabulary of commands that it has, or arsenal of commands that it has. It is, however, very conducive to human beings interacting with the computer. The thing that this paper posits, and there's a little bit of my interpretation perhaps, but I think I'm largely speaking or representing the authors correctly. What they are trying to say is that, see, the standard interface with the bash for command line, and of course, by extension, let's say the GNOME interface or the KDE Plasma interface, these are all human-centered interfaces. They make it very efficient for human beings to engage with the computer to get things done. Now, let us focus down to one particular task. That is the task of programming. Imagine that you're a software engineer, and as a software engineer, you have to write code, you have to edit code and fix bugs, so on and so forth. So you spend your life, if you were to do it on the bash shell, you would open up an editor, you would find a file, you would open it up in some editor, let's say VI editor or Emacs, or whatever it is. You would edit a few lines, you'd search for what you're looking for in that file, and you would edit it, and then you would hope that you have fixed the bug, right? Or fix the issue. But the main thesis that this paper makes is, if we treat as language model agents as doing the task of, if you want language model agents, LLMs, to be good programmers, which is one of the driving forces today. People are pushing very hard to generate code using LLMs, to find bugs in code, and so on and so forth. There are all of these projects around. And they do have a certain degree of success. Like, for example, you can install an LLM on your shell, and on the shell, you can talk to it. You can just paste it some code in the prompt, and you can say, explain to me what is wrong with it, or what should I do? So there's a lot of back and forth from a textual level, but it's clumsy. That interface is clumsy when it comes to the large language model. And the question this paper makes is, what if we created an interface that was as convenient for the language model agents as, for example, VS Code is for us? We use an ID, right? We have a very nice interface which has a debugger, which has a way to open file, navigate file systems, edit code, fix, do things. That is very human-centered. What if we created an interface that is the agent-computer interface, ACI, that is from the ground up designed for a language model agent to engage with code, right? So imagine a Visual Studio Code equivalent, but it is meant not for us, but completely optimized and thought carefully from the ground up for language agents, LLMs, LLM agents, to reason, navigate, and work with code. Right? So that is the main thesis of this paper. Right? And what they show is that if you were to create such an interface, which they call the ACI, the agent-computer interface, then and then you work with that to look at code bases, then there are many benchmarks. These benchmarks look at how well different tools are able to fix issues in code. And what they find is that this approach with a tool, with the ACI, it literally beats the state of the art in almost all the cases. And it achieves a new state of the art. So obviously, such a paper got a lot of attention. It got a lot of attention for two reasons. Practical reasons. Well, it just turns out that this is the right way to use agents, AI agents, to navigate, work with your code, fix it in an automated manner. Because obviously, if you succeed in doing that to a high degree, by the way, at this moment, we haven't reached there. It's still very much a work in progress. But should we say that in an asymptotic limit, someday you reach 90%, 95% success rate, or 100%, close to 100% success rate. Obviously, code and the creation of code and the maintenance of code and the evolution of code would become far less expensive than it is today. Software engineers are and continue to be perhaps one of the highest paid professions in the world. So, so that's the context. Now, with that context, let us read this paper and go into it. So that is one aspect of it. It brings efficiency from a very practical perspective. From a more theoretical perspective, it brings about a new idea. It says, which in hindsight looks like a no-brainer, actually. It's a deep and insightful idea. And the moment you read this, you feel, well, yeah, this certainly should be the way we should go about it, which is that if LM, language agents, AI agents are talking to code, shouldn't they have an interface that is native to their way of thinking, their way of reasoning, and their engagement with the code repositories, with queries, and so forth? Okay? So that is at the level of the thought, that is the main idea. So with that preface, let us go now and read this paper. So today, as I said, we are going to read two papers. So because we are reading two papers, I will stick to only the big ideas. And these are can be somewhat longish papers. I will defer some of the details or skip some of the appendix details and defer it for you to read subsequently on your own. So with that, let me give me a moment to situate myself. All right. So language model agents are increasingly being used to automate complicated tasks in digital environment. So that, especially in 2024, that's very much true. Just as humans benefit from powerful software applications, such as IDE, Integrated Development Environment, for complex tasks like software engineering, we posit that LM agents represent a new category of end users with their own needs and abilities and would benefit from specially built interfaces to the software they use. And I think that is their punchline throughout the paper. So I'll just highlight this big idea that they bring. And this is the idea that the paper develops and investigates and proves that it really is so. It is a good direction to pursue. So let's continue. We investigate how interface design affects the performance of language model agents. As a result of this exploration, we introduce SWE Agent, a system that facilitates LM agents to autonomously use computers to solve software engineering tasks. Note the use of SWE, which is sort of the acronym for software engineering in Silicon Valley. I mean, throughout our profession, I shouldn't say Silicon Valley. SWE agents, custom agent computer interface, ACI, that's an acronym they create. So I'll just park it on the side. ACI, agent computer interface. significantly enhances an agent's ability to create and edit code files, navigate entire repositories, and execute tests and other programs. We evaluate the SWE agent on SWE bench, and so they have their own benchmark, and human eval fix, achieving state-of-the-art performance on both with a pass rate. Pass at one means at your first attempt, you get it right, you fix the problem, of 12.5% and 87.7% respectively. Right? So far exceeding the previous state-of-the-art achieved with non-interactive language models. Finally, we provide insight on how the design of the ACI can impact agents' behavior and performance. Now, this number, in case it doesn't look very impressive, sorry, I should highlight it. In case this number doesn't look remarkable, to put it in perspective, the current state of the art is about 3%. Right? And so the SWE bench is a rather stringent benchmark. The human eval fixed benchmark is not like there it performs better. To say that it achieves close to 88% pass at one rate is quite impressive. It means that it can find and fix a lot of issues. So now let's read this thing. Recent work has demonstrated the efficacy of LM agents for code generation with execution feedback. However, applying agents to more complex code tasks like software engineering remains unexplored. To solve the programming tasks, LM agents are typically designed to use existing applications, such as the Linux shell or Python interpreter. However, to perform more complex programming tasks, such as software engineering, human engineers benefit from sophisticated applications like VS Code with powerful tools and extensions. Inspired by human-computer interface, HCR, studies on the efficacy of human interfaces for humans, user interfaces for humans, we investigate whether LM agents could similarly benefit from better designed interfaces for performing software engineering tasks. Right? That's the main thing. And so this is the main thesis. What they're saying is, suppose you have a language agent here, instead of it directly asking it to use the Unix shell commands, for example, terminal commands, and navigating the file system using what we use to navigate, right? And if you just to put this in context, these days, what do we do? Many of us would either use some Copilot, or you would go to ChatGPT, or you would go to Cloud or something like that, CloudSite or something, or Gemini, and you would say, write me a code to do this, or here is a code section. And then it doesn't really have access to the code except what you're giving in prompt, right? And so the whole process is a little clumsy. And it is not quite agentic thinking in which you can back out and let the agent interact directly with the code base. So it goes on to say, so what they are saying is the main contribution is this. And LM-friendly commands, let's come up with, just like Bash shell has its commands friendly for human beings, let's come up with LM-friendly commands. And when those commands execute, the response, let us have the response in a LM-friendly way from the environment. Or simply put, for example, you can have it as a structured JSON, right? So it can understand. So that would be one example of that. So let's continue with that. It goes on to say, consider the simple setting of an agent interacting directly with the Linux shell. In practice, we find that LM agents can struggle to reliably take action in this environment. For example, it fails to provide simple commands to edit a small file segment and does not provide any feedback if the user makes an invalid edit. So for example, if the LLM says, okay, go make this change, but if the user does not do that edit, but does something entirely different, the language model doesn't know, right? So that's the poor interface that we have at this moment. So these deficits substantially hamper performance, motivating the need for an agent-computer interface, and so forth. So that's what they built. And I won't go too much into the technical details. I mean, see, it's good they have done it. They have given a lot of careful thinking. By the way, it's an area of very active area of research. I will skim over some of the details, but for example, in the ACI, you have a file viewer, a file editor, a code search, right? You can search through the code, and of course, you also can edit the code, right? So what you're basically saying is that an language model, the agent, this is the life cycle of an agent, right? This is how they engage with the ACI. They don't engage with the computer, they engage with the ACI, right? Agent computer interface. Just as human beings in reality, you don't engage with when you deal with the computer, what you're really dealing with are things like PyCharm or Visual Studio Code or things like that, or Bash shell, right? If you look on the right. So figure 2, the caption says, specialized applications like ID make scientists and software engineers more efficient and effective at computer tasks. So most of us believe that we should use an IDE. There are still some diehard who, out of a sense of macho or something, say, no, I still code using VI or something like that, or just a text editor. And I've never used it. I will never use an IDE or debugger ever, right? Somebody once said that the only debugger I've always used is print statements. Right. So, well, there are certain people like that, and it works for them. Usually, these people are the very best because that's why they're allowed to do that, because they can get away with it and they are productive with what they know how to use. But the rest of us, ordinary people, we all use VS Code. We all use some form of IDE, Emacs, PyCharm, VS Code, whatever. So they're saying, similarly, ACI design aims to create a suitable interface that makes it so. Now, I will sort of do a fly over some of the territory. And they come up with certain goals or principles. In this paper, we assume a fixed LM and focus on designing the ACI to improve its performance. This means that we shape the actions, their documentation, and environment feedback to complement an LM's limitations and abilities. What are the limitations of an LM? First of all, you have to worry about the context size, the memory, etc., etc. Right? And the fact that it can hallucinate and whatnot. We draw inspiration from the field of human-computer interfaces, where user studies elicit, etc., blah. We use two approaches to enhance performance on a development set: manually inspect agent behavior to identify difficulties and propose improvements, and run a grid search to select the best ACI configuration. So they did a lot of thinking and planning to get to it. But I'll just mention the 4 points that they've mentioned. First, they say that in the interface, ACI, agent computing, keep the actions simple. So remember, if you remember the paper, React, agents do what? They reason or have a thought. Another way to do it, have a thought. They act. That leads to action, some action, right? They do something. And for action, they may do it on their own, or they may do some function calling. So always remember that they do this. And what they are saying is that for it to act, make sure that the tools that your ACI gives, they should be simple. Those actions should be straightforward. And they contrast it with bash command. So for example, a typical command on the bash shell, for example, even simple things like ls, it has many options, isn't it? You have to read the man page or the info page of commands to know about all the options possible, right? So there is a tremendous amount of power behind every command in the bash shell, usually. And it is in the options. But here they eschew that and they focus on the simplicity. They prefer simplicity. They say simple commands with fewer options and concise documentations are easier for agents to use, reducing the need for demonstrations or fine-tuning. This is important. You realize that if you have lots of options, there would be a combinatorial explosion. You'll have to document so much. And you may start exceeding the context limits and other aspects of a language model, right? So it says, keep the options fewer. Each of them give concise documentation. So And for those of you who are using practical agentic frameworks, for example, Crew AI, you know what's the basic thinking? Role, set a goal, set a backstory, provide context, and so on and so forth. Okay? So it's pretty similar to that, but what they are saying is keep it simple. They say that this is a defining principle of all SWE commands. The second thing is even the action should be compact and efficient. So make the action sort of atomic, things like file navigation, editing. Don't make them very complex actions. Should be considered into as few actions as possible. Efficient actions help agents make meaningful progress towards a goal in a single step. A poor design would therefore have many simple actions that would be composed across multiple turns. So in other words, don't do it like that. Right? Environment feedback should be informative but concise, the opposite of it. Your responses from the environment that the agent gets, the output of your commands, if you think of it as an AI agent, when you do something, the output that you get from the environment or from the ACI should be informative but concise for a similar reason, right? Then guardrails mitigate error propagation and hasten recovery. So this has to do with the fact that, see, when this is, and I'm jumping a little bit ahead in the paper, what happens is if the machine makes a small mistake, it replaces a code with what it thinks is a fix, but that fix doesn't work. It tries to use a Python interpreter, let's say, to run the code and realizes, oops, that's not correct. Or it evaluates itself. It does a self-reflection, says, okay, that doesn't work. It will then change the code again. But what can happen is you can have a cascading of errors. One error will lead to another error, will lead to another error. And so it may get pretty bad. So they have guardrails to recover from such code syntax. And that automatically detect mistakes, and then you do that. So what can we do? For example, a very easy thing is just use a linter, right? That's what we do in our VS Code, right? And most of you use, I don't know, some form of linter at least. You use something that will give you a hint, a compiler, linter, something that will give you a hint that your code has errors. People use Sonar lint, or they use rough, or pick your favorite linter. So why shouldn't the AI agent also do that? And the experience is if you put such guardrails to give hints to the agent that the code may not be correct, they actually do very well and they recover very well. Now, the way this agent works, the rest is details. They have in their interface, they have special commands like find, search file, search directory, right? Etc. etc. And when they edit a file, what they do is they take a small window into the file. It's a paginated view. You can page up, page down, but you don't get the entire file content, especially if it might arbitrarily span 20,000 lines of code, right? And as you know, in some languages, C, etc., people often have giant implementation files that can run 20, 30,000 lines. So obviously that would not serve the purpose. So you get a small window into the code. And what it does is it keeps saying next, 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 till it finds what it's looking for. Right? Now, you may say that, okay, what's the big deal? Let's step back and ask, what's the big deal? Haven't we been using RAG to do a similar code analysis? Given a query, you can index all the source code, you can do RAG, and you can bring it up, right? So that part is okay. The problem is not the search and the retrieval, but is the fact that it is not very efficient and able to fix issues or identify issues so well. As the benchmarks will show, these things do better. Right. So that is the main thing. There's an experimental setup and so on and so forth. I wouldn't go into that. Suffice is to say that it has very good compared to RAG. If you notice, for example, if you use RAG with GPT-4 Turbo, the state-of-the-art GPT at the time of this paper, I think 4 just came right after that. At that moment, with RAG and GPT-4, and you could fix 1.31% of the SWE bench errors, right? Resolve the issues. With Cloud 3 Opus, you could do practically 3 times, 3.79%, right? That now, when you look at what it can do with SWE agents, you realize that this is a vast improvement. We are not talking about compare this to this. Do you see that this is a vast improvement? And it is as resounding an endorsement for this approach as can be, experimentally or empirically, isn't it? Similarly, they have a slightly different version of the benchmark. There too, their resolution rates, look at this. Right? Now, what is the trade-off? Because your machine is reasoning, thinking, react, and going back and fixing it, correcting itself, self-correcting and all that, your general cost goes up. So the price that you pay is in terms of slightly higher price. Look at this. Here you're paying 13 cents and 25 cents. And here to fix issues, you're paying on average $1.50 or $2.50, $1.60 or $2.60, isn't it? So obviously you get a higher pay rate. But frankly, guys, if all it takes to fix an issue is $1 or $2 or $3, would you rather have that, or would you get a bunch of engineers and say, okay, 1 week sprint to fix these? Right? 2 week sprint, 1 whole sprint to fix these, right? Which is the norm today. So obviously, these numbers, when you put it in perspective of what it costs today in terms of human cost, these are almost negligible. These are rounding errors, zero. Right? Likewise, on the human eval fix, another benchmark, notice how much better it does, in particular compared to such things as just about everything else, like let's say GPT-4, for example, right? Or a DeepSeek coder and Wave coder and all of those things that people have been creating, which they have been fine-tuning language models, especially to deal with code, right? Code generation, code evaluation, code fixing, and so on and so forth. And the SWE agent using GPT-4 as is, without any, because of course you can't go and tune GPT-4, right? You just use the API calls. Just using the API calls, but the whole SWE agent architecture is an architecture that says, let's create a good interface and let the agent, language agent, interact with the interface, and the interface interact with the environment, right? So just by doing that, they achieve impressively high improvements in these, right? Which is why it got, and then this paper goes on, and I will skip that. There's a lot into this paper, but I will skip the rest of it. Needless to say, this paper, at least in the Princeton University circles and those areas, has garnered a lot of interest and a lot of industry interest, actually. And people are taking it quite seriously, and they believe that this idea is certainly a part of a bigger idea that can be built up around it. So that finishes our discussion of the SWE agent paper. Does anybody have a question, by the way? Go ahead.
So,
Microphone.
this,
Good microphone.
yeah. Hello.
Yeah.
So in order to have those benchmark numbers compared against the rank model, so I believe these guys will be generating some kind of a code that they injected some error conditions and they are feeding into different model to get the benchmark, right?
Absolutely.
Okay.
That's what they do. So, and see, good news is SWE agent represents quite an improvement, right? At least on the SWE benchmark. So their benchmark is stricter. On the human eval benchmark, it's doing very well, 90%. Certainly. Their own benchmark, which must be made up of rather tough cases, it found that other models are at 1, 2, 3%, and they are at 10, 12%, which is an improvement. Nevertheless, it also points to the fact that there is a long distance to go. Any other questions, guys? Anybody else?
One more question.
Mm-hmm.
So, do they have written some kind of a program in order to mimic this agent?
Oh yeah. There's a. I mean, if you want to get into the details, here are all the prompts and the commands. Here's the creating all of that. All of the details actually are here. Right? See, at the end of it is prompt engineering, right? Systematically thinking through and prompt engineering and a very effective use of prompts and creating an agent with that. But it's very care. See, at the end of it is the architecture, just like software engineering. At the end of it, code is code. But companies or products live or die by how neatly it is architected and right and how powerfully it's architected. So the same idea is here, right? So you can see configuration YAML, prompt templates, everything is here. This paper actually is just 10, 12 pages of the main ideas and long amounts of details. And these details are pretty extensive. As I said, I'm not going into them, partly because it can keep us busy the whole night. Right? It's very good, actually. So you can see how well the agent is thinking. This, if you remember the React, reason and act, we covered that. It is thinking through very well. It's making observations, thinking, right? Observations, thinking, right? So it's a classic. So they have given essentially the trace of the engagement, which is what makes this paper very long. And if you read it, you will notice that the thoughts that it's having are pretty good. Right? It's pretty well thought out. All right, so that is this paper. Now let's go to the next paper. Would you guys like to take a 5-minute break, or should we start on the next paper? 2 minutes break. Okay, let's all take a short break. Guys, those of you who are remote are rather quiet. Any feedback? I don't know. What did you think of this paper? The first one, SWE Agent.
Hey, Asif, this is Chris. First time here. Thank you so much for being so articulate. I'm enjoying the session so far.
Oh, thank you. And welcome to Support Vectors. We do have this paper reading every Wednesday, even if you forget to inform till the last minute, like today.
Perfect. Thank you.
My name is Alexander. I also first time here, so very interesting paper and some very interesting research.
Thank you, Alexander, and welcome again to Support Vectors weekly paper reading. If you are in the, where are you? Are you local? Or are you in the Bay Area or remote?
Yes, I'm on East Bay right now. So.
Oh, okay. So we are not far off. We are in Fremont, next to the Tesla headquarters.
Yeah, I will try to come next time.
Yeah, perhaps. Nice. And all right, guys. So we'll move on to the next paper now. It is called XLAM. So these days, you notice that the large language model, the LLM, is being there are different adaptations or variants of that coming up. For example, large vision models, right, are coming up. And this is large action models. Whenever people use the word action, you should think agents, because it is the quality of an agent to reason and act, right? To have a thought and then to use to engage with the environment, receive information from the environment, well, the old words would have been sensors and actuators, but today we would just say it uses the tools and it gets a response. The response that it gets, feedback, is the equivalent of the sensor, and the things it does with the tools are the function calls, right? It can do a lot of function calls. So that is it. So now let's read this paper. This paper too, this paper is very recent, even more recent. Just came out a couple of weeks ago, if that. And it came out of Salesforce. Quite a few authors. And it's, I would say, a good paper and fairly straightforward from a theoretical or conceptual perspective. But it must have been a tremendous amount of hard work, because basically they have put in Herculean effort to create good data sets and good benchmarks, and then train a model, and found that if you do so, your model becomes very good at agentic reasoning. So we'll read this paper. Autonomous agents powered by large language models, LLMs, have attracted significant research interest. However, the open source community faces many challenges in developing specialized models for agent tasks, driven by the scarcity of high-quality agent datasets and the absence of standard protocols in this area. This statement is the crux of it. It is a huge problem, as you know. For example, even when companies these days so-called open source their model, what they're giving you are the open weights. None of them are giving you the data they train those weights with, isn't it? They'll tell you the architecture, they'll tell you the weights, and then you ask, okay, what about reproducibility of that research? And they'll say, oops, no, we're going to keep the data to ourselves. So the open source community has obviously been somewhat starved of good data set. And recently, there has been quite a bit of effort to gather good data, especially in a cutting edge field, literally at the bleeding edge, which is agents, AI agents and agentic reasoning, or multi-agent systems, MAS, as that acronym is evolving in MAS. You notice that it's very hard to get benchmarks and large data sets to train them with. Right? So here comes their contribution. So here, the first contribution that they make is here. We introduce and publicly release XLAM, a series of large action models designed for AI agent tasks. So remember, it is specifically meant for AI agents, right? Or to be used to do this interleaving of thinking and acting. How will it act? By making the right function calls. So what would you do? Thinking is something that LLMs do. But to be able to, from that thought now, figure out which is the most relevant function call to make, and to make it without hallucination, right? Or so in how many ways it can go wrong? For example, it can say, suppose you tell it that you have functions A, B, C, D. It may all of a sudden say, okay, I need to invoke function X, but X is not even there in the list that you gave it. So that would be one form of error, and LLMs make such errors all the time. The second error that it can make is, it can say, okay, I'll invoke A, but suppose A, the signature of A says it takes an integer, right? It may actually give it a wrong. It may actually say, I'm going to invoke A with a string, right? And that would be wrong, or with a date, or something like that. And that would be wrong arguments. And the third way that it could be wrong is it can say, well, the signature of A was just one variable, one parameter, but it may decide to pass it 3-4 parameters. Again, all of these are non-starters from a programming perspective, right? The interpreter will just throw it out. And so these problems have been there with LLMs. They do hallucinate. They do create these nuisances. And many of you who have been trying to use this, and here, for example, some of you who were here with Agentic course before, remember that we played with the Gorilla LLM in the whole work from Berkeley, the excellent work from that. So, well, we'll come to that shortly. But the contribution of this paper is it wants to create a fine-tuned LLM, or rather they call it LAM, large action model, which is specifically meant for agentic reasoning or agentic tasks. And how do they do that? They use two models. So there are two ways that you go about these days doing it. One is that you can take a model. Let's say you take Gemma or you take Mistral or something like that, right? Llama, and then you fine tune it. And these models are called dense models, as opposed to so-called sparse models, a mixture of experts. What are mixture of experts? What you could do is you could take multiple models and front them with the router. So it's a mixture of experts in case you're not familiar with. So the idea is that suppose you take a model. Here is one way to think about it. Imagine that this model is a chemist. This model is a biologist. This model is a physicist. And this model is a mathematician. Right? And let's say there is a model that's a generalist. So what you do is that when a query comes, you need a routing network, routing neural net, that just determine, and I'm giving an oversimplified way. In reality, what happens is that you have multiple chemists and multiple biologists and multiple mathematicians and so forth, something like that. So one intuitive way that you can look at it is this routing network has only one thing to decide. Who should the routing network give the query to? So suppose the query was, right, why is the sky blue? Right, it could be. So it may decide, and that is query 1. And let's say that the query 2 is, what is the difference between I'm sure I eukaryotes and eukaryotes. And then query 3 would be explain the now. So clearly, we can read it and we can say, aha, query 1 certainly, who would be best? You would say, all right, this perhaps we are best served if we give it to the physicist, right? And then when it comes to query 2, we may say that we are probably best served if we give it to the biologist. And for query 3, we may argue that we are best served if we give this one over to the mathematician. Does it make sense? And that is the job of a routing network in front, right? So when you do that, what's the benefit of it? And why are these called sparse networks as opposed to dense? So this is the concept of mixture of experts. This comes from an original paper written by Jeffrey Hinton many, many years ago. So advantage is this. See, when you have one ginormous model, the query will go and the signal transduction will be through everything in that neural network, isn't it? Every single thing. Even if they are dead neurons, you can say, all right, the matrix is dead. But nonetheless, in principle, the signal transduction is through the entire dense network, isn't it? So a lot more computes happen. The big model will lead to big compute. On the other hand, if you have a mixture of experts, you realize that you can have your chemist, biologist, mathematician, physicist, etc. They could be relatively smaller models, and a query goes to only 1 or 2 of them, isn't it? When it goes to only 1 or 2 of them, the rest of the networks are not even activated in the forward pass, in the inference phase, right? The routing network, which is usually a pretty small network, just figures out who to give it to. It gives it to the network. And the physicists, the mathematicians are relatively smaller. They are not know-it-all, know-it-all oracles. They just need to be good in their own subject. And so they are also smaller networks. So you have more efficient utilization of resources, and these are sparse things. So obviously, these days, mixture of experts has gotten a lot of attention and utilization and adoption. We here, for example, at Support Vectors use them pretty extensively. So let's continue this. The LLM series includes 5, so that explains this thing and therefore the digression. It uses both dense and mixture of expert architectures. The way to read it is, dense is one model, mixture of experts is lots of models fronted by a routing network, right? Ranging from 1 billion, so 1 billion dense model to 8 cross 22 billion, which is the largest. What does it mean? 22 billion parameter experts. And how many experts? 8 experts, right? And of course, with a fronting routing network. Trained using a scalable fixed pipeline that unifies, augments, and synthesizes diverse data sets to enhance AI agents' generalizability and performance across various environments, and so on and so forth. And then one of the things it makes is that in this space, in agentic reasoning, one of the benchmarks that's quite important is the Berkeley function calling leaderboard, right? And it is not a joke to come up with something that outperforms GPT-4 and cloud, which are the state of the art, right? Because if you notice, go to the OpenAI's webpage, they also are beginning to support function calls and so on and so forth. So this is the key. As always, you have to say that your approach not only is good, but it leads to demonstrably better results and achieves a new state of the art, which it does. And then they release their model. They release 2 things, model, and also they release the data set. Actually, I would say that the other contribution is just as important. In the open source community, there's a scarcity of data, and they have taken quite some effort by harmonizing all these data sets and bringing it together and creating generally a good benchmark. So there have been benchmarks that they have created, and here is a picture, and I'll just sort of skip over it and go straight to the contribution. So they do mention that this task actually, it's a task, like in hindsight, it looks, okay, great work, and they achieved good state of the art. But when you really look under the covers and think how they must have done that and what the current situation is, how frustrating the current situation is, but then you realize that these people have really, really worked hard to bring this about. That's my guess, right? So they go on to say, recently, the agent research community has intensified efforts in open source agent data processing and model training. However, these works still face challenges in managing complex environments and generalizing to new scenarios, primarily due to the limitations in collecting agent data. So the stifling problem is data. A major obstacle is the homogeneity of content and formats in existing data. What it means is that you'll get one data set, and all the problems that you will do, all the tasks in there, will refer to, let's just say, coding, right? Another will exist, and it will all be like web surfing, like e-commerce. Imagine asking an agent to go buy things for you from Amazon, right? So there's a certain homogeneity or siloed nature of each of this, a very specialized nature of each of these data sets. And so resulting in models that lack diversity across various tasks and struggle to adapt to new or slightly different data structures in practical terms. So, the thing is, if you have very specialized data sets, all you can say is, I can train a model that will be good at that task, rather than a general purpose AI model, right? And because a general purpose AI model needs to do many things, right? It should be able to generalize beyond the specialized task. And that is the problem. So they go on to say, while previous efforts have attempted to design pipelines for unifying data, they typically cover only a few scenarios or lack flexibility in their uniform format. So this is sort of a critique of where we are today. For instance, blah and blah. So I won't go into that. Then it goes on to say, moreover, open source datasets often suffer from quality issues such as incorrect agent output, hallucinated actions, and repeated interaction turns within trajectory. So what it says is that actually, if you look at the data set, the quality is somewhat low, right? Ideally, the data set should be gold, right? So for example, if you're talking about images, well, not here, but in a different context, then a bird should be called a bird. It shouldn't have been erroneously called a house, right? Or a book. But so that's an error, categorization error. So what happens here is what they are saying is that they found that they had error. So they have created a process of all of these things they do. First, they do data unification from all these different things. Then they do quality verification and fixing where possible and filtering out what is unfixable, right? To create. Then what they do is they do data augmentation by using prompts and instruction following and so forth. These are pretty standard techniques that I would imagine most of you are using nowadays. And then data mixtures. They mix it up. So how would they mix it up? For example, if you're listing functions, function callings, tools, just give it in different order, shuffle it, right? Don't always give the same order of tools, right? But you can do other things, right? You can even give the arguments in different ways, things like that. And put the instruction before this, change the order of the instructions, and things like that. So you can do some bit of internal permutations. Then after that comes the actual. So at the end of it, up to above this line, it is all data level activity. This is their Herculean effort to pretty much have good data. What can they do after that? What they do is and then there is also another effort, a data synthesis, right? So you can take some good APIs and then use LLM to synthesize lots of data to train the model. And these days, it's a given that when we train the model, we often create synthetic data to train it. So they do a lot of synthetic data creation. Now what happens? They do, now just to remind you, what is the instruct fine-tuning, the instruct tuning of a model? The phases are usually these. You first take huge data, and you create a monster, the pre-trained model. So, and for reference, I would recommend that you read the Instruct GPT paper. It's a classic architecture. You do that. Then you do, next phases, you do supervised fine-tuning. Supervised fine-tuning can only be done with small data because it's hard to create labeled data. You say that if this is the prompt, this is what the output should be. Are we together? This is what the continuation should be. And when you do that, you can use a causal loss function, right? In other words, how much does the output depart from, token by token, depart from what you expect it to be, right? And you create a loss function there. So it is supervised fine-tuning. After that, the next phase is you do human feedback alignment. Right? The human feedback alignment, if you remember, in the original time, it used to be done with PPO. That is reinforcement learning. But actually now, the preferred approach is DPO, direct preference optimization, which is actually not de facto, it's not a reinforcement learning. It is sort of a latent form of reward model that it creates, and so does exactly what reinforcement learning can do. But people still sort of popularly or sloppily think this too is, well, all right, reinforcement learning. So based on how strict you are, you can call it reinforcement learning, or you can point out that this specifically is not reinforcement learning. So that speaks to the that speaks to the DPO, direct preference optimization. Oops, what am I doing this? Okay, much better. This. Now, so SFT is the supervised fine-tuning. Let me put those words there. Supervised. Fine-tuning. And DPO is the direct preference. What preference? The human preference. optimization, which basically is a fancier word for alignment. Now, you notice that in brackets, there are two words, full and LoRa. What they are referring to is that you can either sort of unfreeze all the weights of the pre-trained model. Suppose you take a model, let's say you took Mistral or you took anything, Llama. You can unfreeze all the weights and then fine-tune on your data, but that can get, what's the risk of fine-tuning a full model? The demerits are that A, it's computationally brutal. You need to all of a sudden find that you have lots of H100s lying around, idle, right? And the second thing that you need to make sure is there is a genuine risk of catastrophic forgetting in the full SFT. There's a risk of catastrophic forgetting. What this means is that the model may at some point decide that whatever it knows, perhaps it needs to jettison and adapt to the new reality, right? There's always a risk in full fine-tuning. And it happens when your fine-tuning data's distribution is too different from the original data distribution on which it was pre-trained, right? So catastrophic forgetting. On the other hand, if you use LoRa, LoRa's advantage is you don't touch the full model at all, the pre-trained model at all. You just train a low-rank adapter. In other words, you train AB matrix and the weights associated with AB matrix, right? One matrix downscales it to a latent space, another scales it back up. But in the whole process, you have lots of weights here. And these are the only weights, a very small number of weights that capture the fine-tuning. And it comes from the fact that the fine-tuning has to be small perturbations of the original weights, and they should be representable as a low rank or low dimensional space within a low dimension space. That's the sort of the mathematical nature, but let's not get too much. The advantage of LoRa is, advantages are, it is very easy to fine-tune, quick, low resource requirement. B, second advantage is you do not fear catastrophic forgetting at all. Why do you not fear? Because you're not touching the original model at all. The original model continues to be frozen, right? The disadvantage of LoRa is, as many people point out, that sometimes it is not as accurate. Quite often, it leaves something to be desired with respect to achieving the last ounce of accuracy or model benefits from fine-tuning. Right? And so again, LoRa's are a very popular form of performance efficient fine-tuning, but it's there. So they said that they use all of these approaches. And then they feed it into the model benchmarks. Using the benchmarks, they often also do some data verification. So this is the main flow. What did they achieve? So there's data processing here. And what they find is something very interesting. Let's look at the tables now. And I'll only go through the figures now. Look at these figures. Overall, an overview of the XLAM model performance on the Berkeley function calling leaderboard. Right? Function calling is at the heart of, well, I suppose, core of the agentic reasoning, agentic model. You have to do something, right? Not just think and talk with these models. So these are action models. So you notice that they got the data here by their state. Now observe something. If you look at the small model, so this is the domain, you notice that these are all small models. These are 7 billion, 8 billion parameter models. On one particular Berkeley benchmark, what is their overall accuracy? It's around 65, isn't it? If you look at the numbers, it's around 65. Let's take, and then what they have done is, if you notice carefully, they have put the commercial models here, just as a reference. So Cloud 3.5 Sonnet on the 20th of June, 2024, it was achieving a little less than 70% quality. But then came for agent, because it's a general purpose model, so you would expect that. Then you have a few Commander R plus and this and that. You notice that you're creating models which are significantly bigger. Now look at these models. And if you look at the scale here, look at this and this scale and this scale. What does it say? It's almost 100 times bigger, isn't it? Commander R plus, etc. They're approximately 100 times bigger or 50 times bigger, whatever, 2 orders of magnitude bigger, more, give or take, or one, at least 1 order of magnitude bigger. They do achieve for you between 70 and 75% accuracy. And here comes the interesting punchline. Gemini is at 75%. And look at the smallest XLAM. So they release a whole series of models of increasing size. Their biggest model, and let me use a different color for their models. So their biggest model is here. You notice that for agentic tasks, it beats just about everything, right? It does very well. It beats GPT-4, it beats Cloud, it beats Gemini, it beats, well, okay, all the big frontier models it beats. But of course, only for agentic tasks.
Specify like what exactly? Because they say that they're 1 billion each. I think like the original 3.5.
Only for agent tasks, which means selecting the right functions. Fine tune on that. Remember that these are action models. They focus on one task and one task only, right? And so it makes sense, right? It's better. And so you can see where these guys are landing up, and they are doing impressively well. Now, one of the other contributions of this paper is not just that they built a lovely model. They actually ended up creating a remarkably good data set that they have released, and so we can all benefit, right? So they're related works, and so they've done data unification, augmentation, and so on and so forth. And they've done a lot of good things, and the results are pretty good. I won't go into it because I noticed that I've already exceeded my, I'm 4 minutes to my time. So the important thing is to look at the benchmark. So a web shop is a benchmark which gives you an e-commerce experience. Observe that even a tiny model like 7 billion LAM beats, by the time it seems GPT-4o is released, GPT-4o, right, on this kind of a task. But none of them, so there's something to be said, none of them at this moment on a tool query, like at this moment, beat GPT-4o preview. None of the XLAMs do that, but they come pretty close. Do you notice that they are second best, right? For models that are so much smaller, 8 cross 22 billion. Isn't that pretty impressive that they can come that close, right? They come pretty close to it in total. And likewise, there are other benchmarks, unified, there's a unified version. And then you notice that it achieves state of the art and so on and so forth. So I'll let you read the details, but how often do they do the right thing and the pass rate on the tool bench in 3 distinct situations? You notice that usually it is either best or second best. So for example, here GPT-4 does better, unseen tools, things like that. And sometimes it doesn't. So I will leave it. Those are, again, the benchmark results. They have done ablation studies to say, you know, to train this model, to go through that fine tuning of the models, they use 3 techniques, at least 2 techniques, augmentation and cleaning of the data, right? So how much did each of those factors contribute? They say that if you don't do either data augmentation or cleaning, then the base result is the deep blue result, raw data result. And then if you add augmentation, you get about 2.3% gain on the tool bench. And if you add cleaning of the data, you get a significantly 4.6. By the way, there's a larger thing that's emerging these days. People are finding that the data on which we are training our models are rather shabby, noisy. And one of the things that people are saying is, let's try to clean the data, put more effort in cleaning the data and have much cleaner data, right? And in fact, if you remember, there are the whole of the 5 series, 5.1, 5.2, 5.3. It started with the paper, textbooks is all you need. Why? Because textbook is practically the benchmark of how good text can be on a topic with which you train. And when you train a tiny model, very tiny model on just very high quality data, you get very good results. So you can see some connecting the dots from that to this. And thus, we come to the end of our, and then you can go and actually read the prompts. And that is it. That is this XLAM paper. So I hope you enjoyed this journey into AI agents. Any questions, guys, before I close the recording? Anyone, any questions? No questions. Okay, I'll stop the recording. Where is it?